Hey guys, previously we talked about basic acid-base neutralization reactions. What we're going to be looking at now is basically that third type of reaction I showed you in the review today, where I basically was saying that you don't see salt and you don't see water, but that doesn't mean that it is a neutralization reaction, or it doesn't mean that it isn't considered an acid-base reaction. So I'm kind of just calling this other acid-base reactions. What you're going to notice most of in this section is going to be learning about the actual transfer of the hydrogens, as well as a little bit more vocabulary. So as mentioned previously, water actually has some unique properties. We know that water is just weird and incredible in a lot of different ways. One of them is that actually it can act as an acid or a base. Okay? Now, that seems weird, but when you learn on the next slide really what the actual definition of an acid and a base is, it'll be pretty clear why it's like that. So water acts as both an acid and a base, and you'll notice here that we have two waters here. And if one of the hydrogens from one moves over to the other, then we create hydronium and hydroxide. So we're saying that water has the ability to create hydronium, which would decrease the pH, and water has the ability to create hydroxide, which would increase pH. So it has the ability to do either depending on really what it's with. When it's by itself, it does a little bit of both, which means if you add a little bit and subtract a little bit, you end up with nothing. Right? So if you try to raise the pH and try to lower the pH, then nothing happens. And that's really what's happening in a normal situation with water. We look at a glass of water and we say, water, cool. Okay? But what's really happening there is that we're getting this reversible reaction here. We're getting water losing a hydrogen to another water molecule and creating hydronium and creating hydroxide, and then shifting that hydrogen back over and creating water again. So you're getting that back and forth. But if you put water with an acid, what you're going to get from that is, of course, the acid will dissociate into its H plus, and in this case, it's Cl minus. Okay, and water, because it's a covalent compound, isn't going to dissociate at all. It's going to just stay as water because it's not ionic. So then what you see is that that hydrogen from the HCl is going to clink onto the H2O, create H3O, and then you're left with your chlorine off by itself. Okay, so as a result, we're going to increase the H3O concentration, which subsequently will decrease the pH. Okay, and we'll learn more about calculating pH and stuff soon, but hydronium ion concentration, the more hydronium you have, the more acidic it is, so you're talking about a lower pH. Okay. So what you're going to see here is that water actually will act as an acid in this case, because water is essentially going to be donating a hydrogen onto the base, okay? And so you're going to see on the next slide what that ultimately, or why that means that way. And that's going to create, in this case, NH4 plus and OH minus. So here's where we get into the really technical definition of what acids and bases are. We know that acids have a low pH. We know that bases have a high pH. But what the technical definition for these things are is that acids are what we call proton donators. So they're going to get rid of protons. And really the proton is the hydrogen plus ion, H plus. Okay? So acids are going to release hydrogen. And so when you dissolve them in water, or when you react with something, they're going to donate a proton. They're going to donate a hydrogen. And when they do, they form what's called a conjugate base. Now I'm going to explain what that means in just a second, so don't freak out. But if you're doing acid dissociation in water, what you're going to get is that it's going to donate that proton onto the water, like in this case, where you get that hydrogen onto the water, and you create H3O, which, as you know, is going to lower the pH. So that's really why the pH goes down when we add acids to water. The acid itself, when it's a powder, isn't really acidic? It's kind of hard to say, but it isn't really necessarily releasing hydrogen ions because it's a powder. But when you dissolve it in water, that's what it's going to do. It's going to release those hydrogens, it's going to donate those hydrogens or donate those protons, and generally attach them to water, creating hydronium, lowering the pH. Bases accept protons. So when you're reviewing or making yourself some flashcards, that's really what you want to really focus on. is that acids are going to donate hydrogen and bases are going to accept hydrogen. So when you're looking at something and I ask, hey, identify the acid, look for what's going to be donating a hydrogen, something that would either dissociate and release a hydrogen or something that just logically is going to donate the hydrogen in the process, or which one did donate the hydrogen in the process. So looking down here at our diagram at the very bottom, we see that the acid is identifiable because it releases the hydrogen onto the water, so it is the hydrogen donator or the proton donator. The water in this case is acting as a base, not because it has, a super high pH or anything else that you have about bases, but because it's literally accepting a hydrogen. That's it. That's what bases do. Okay? Acids donate hydrogens, bases accept hydrogens. So in this case, the water is accepting a hydrogen, creates H3O, and that's what we create. As the H3O, we call that a conjugate acid. Now, the reason we do, notice that we are now calling them something, an acid and a base. Because, oh my goodness, look at that. The reaction is reversible. So what that means is that if I were to reverse this reaction and go that way, guess what would donate a proton? Freaking water. There it is. Okay? So that's why we call it an acid. And we call it conjugate acid because, it's not necessarily the forward acid or the acid in the beginning. It's the acid if we were to reverse the reaction. So if we put hydronium, mix it with chlorine ions, then the hydronium would act as an acid, the chlorine would act as a base because it's accepting protons, and so that's what you would get. So that's what you really want to try to study and memorize. Acids donate protons, bases accept them. So let's look at this particular reaction and let's see if we can identify a couple things in here, okay? First of all, we want to identify which substance is actually releasing hydrogen, which substance is absorbing hydrogen or accepting hydrogen. So here is where I see the hydrogen, and on the other side, I see that that same hydrogen has attached to NH3. Now, even without noticing the arrow, we should have noticed that this substance over here on the left-hand side started as NH3, and now it's NH4, right? We have 4 hydrogens on there rather than 3. So in this case, we can identify that the hydrogen donator was water. That's our acid. The hydrogen acceptor is the NH3, the base, okay? So if I go here, and then I do here, there we go. So now you can see that we have NH3 plus H2O. That is ammonia and water. And again, the ammonia accepts a hydrogen, so that is our base. The water gives off the hydrogen, so that is our acid. So as the substance donates a hydrogen, that's what we're going to see. So now an acid is going to release a hydrogen and become a conjugate base. Okay, and this is going to take some practice to get it right, but don't worry, we have practice. Don't worry. This may get some practice to get it right a little bit, but the substance that released the hydrogen in the forward reaction, if I look at this reaction now in the opposite direction, if I say, okay, I'm looking at it from this direction, starting with OH as a reactant, NH4 as a reactant, the OH is going to accept that hydrogen from NH4 to get back to this state over here. So as a result, that makes it a base. Okay? It's not the primary base like over here, so we call it a conjugate base. And again, the NH3 accepted the hydrogen, so that makes it the conjugate acid now, okay? And the way, and this is just straight up. Sometimes it's hard to remember that a base becomes a conjugate acid and acid becomes a conjugate base, but if you're trying to remember, and I told you to focus on saying, acids donate protons, bases accept protons, so think about the reaction in both directions. Think about it from the reverse reaction, and say, okay, if I reverse this reaction, NH4 is going to release that hydrogen and give it back to OH to make water. Therefore, that means, straight up, that NH4 is the conjugate acid and hydroxide is the conjugate base. Here's a couple more examples, some you've already seen and some new ones. But again, the substance that's going to immediately release the, oh, that ain't right. There's a typo. That's supposed to be a 3. Okay, whatever. So the HNO3 would dissociate into NO2, which is nitrite, and H, which is hydrogen, of course. So that means that it's likely going to be the acid. Water, in this case, in the first reaction, is a base. And so the substance that, on the other side of the reaction, would accept the hydrogen is going to be the conjugate base. And the other one that now has the extra hydrogen is the conjugate acid. So that should be an H3O. Sorry about that. Down at the bottom, this is again hydrochloric acid and ammonia. So hydrochloric acid will create hydrogen and chlorine. Ammonia is just ammonia. And so with hydrochloric acid creating that hydrogen, it would transfer it over to the ammonia. So that makes the ammonia is the conjugate acid, and the base and the chlorine is the conjugate base. Okay. So again, we're going to practice with this. What I want you to really focus on getting from this is acids donate protons, bases accept protons, and once they do that, they essentially flip and become the opposite thing on the other side of the reaction. Okay. We'll practice them so you'll get to see them, and I will see you guys soon.